But I mean, hello, testing. We good? We are good. All right. So I made this announcement at the beginning, but I'm gonna say it one more time. Now that we are officially starting, as Jonathan said, this is gonna be a very interesting meeting. Computer vision is extremely dense. We're gonna be covering a good, decent amount of topics, especially towards the middle and towards the later half of the meeting, that can get extremely complicated. So please show some emotion if you're not getting it. Give me confused faces. Don't give me blank stares. Please, please, I'm actually begging you because it is pretty difficult. I want to help you guys out. That's the first thing. The second thing, this is a discussion oriented meeting. And preferably if you are sitting alone, uh, if you could find someone else who's sitting alone, or if you see someone in a group that you want to join, please join them because it's going to be a lot more of you talking versus me talking up here. It's very different. We want you guys to lead the meeting today versus me. It could give you guys a better grasp of the material rather than me just talking for like a good hour. So that's the first thing. The second thing is for the first part of the meeting, you guys will not be needing your laptops. So if you guys could please turn them down. So we're eliminating the computer part of this computer vision part for the beginning. We just want you to use your eyes, and for actually this first part, your mouth. Oh, where is the slide? You know what? Uh, thank you guys for not being in front, so I can actually just. Perfect. All right. So let's get cracking. Let's get cracking. So that's the wrong button. There we go. Oh, what the? All right, that was the right one. Okay, so how many of you guys are computer science and engineering students? You two are not raising. How many of you do not have a Python IDE installed? All right. Oh, you don't have one installed? Like, do you have like VS Code or Idle or something like that installed? Sorry, say that louder. I can't hear you. Uh, that should be fine. We can test that out later. Do you don't have VS Code installed? You have it? All right, so everyone has something like that installed. Okay, perfect. So the reason I say this is the code at the end does not work on the Collab notebook. It's going to be using your computer's webcam. And a lot of the time, and every time I've tried using Collab with this, uh, there are a lot of privacy issues, so it just can't access your webcam. So we're going to bypass that by going directly to your computer by utilizing your IDE that you have installed. Okay, so with that being said, let's get into it. What is computer vision? What what is it? I want to know from you guys. So I'm going to give you guys 30 seconds to 45 minutes. If you're alone, think to yourself. If you are together, talk with the people next to you. What is computer vision? And give me some, not applications, but give me some not examples, but how can it be used within, like, I'll give you an example, like object classification, something like that. Uh, so what is it? If I want you guys to provide me like a formal definition, kind of, and give me an example of where now you've seen it used, or yeah, just actually, you know what? Just give me a formal definition. I'll give you guys like a minute. Go for it. Talk with your neighbors. I don't want to hear it. All right. So, I'm gonna quiet y'all down. I heard a lot of encouraging discussion. So to prevent me from just picking on y'all at random, Uh, what is computer vision? Who wants to raise a hand or just blurt something out? Yeah, that's pretty much it. All right, what's up? Sure. Can you give me examples of what kind of information you can get out of an image or a video? Sure. Sure. Those are all really good examples. Does anyone else have anything else they want to add? Yeah. That's actually a really good way of putting it, actually. I've never thought of it. I've never thought of it like that. Where how can we do what we do? How can we do with a machine what we can do with our own hands? That's actually a really good way of putting it. And I want you guys to use that as kind of like a foundation for everything that we get into moving forward. Because everything that we do, everything, all these projects kind of relates back to that definition. Like, all right, I want to be able to know that that's an iPad. I want to be able to know that this is my pinky. I want to be able to know how it moves. I want to know all that, right? There's so much information we can get out of images, and there's so much we can do with computer vision that normally that we can do with our own eyes, but we can also make a machine do much better. So with that being said, what are some applications of computer vision? What have you seen? What have you seen? What even better? What are some applications? Actually, no, let's start with that. So what have you seen? I'm going to add a little bit of a twist to it because I know everyone has the same kind of ideas. Like I've seen it in Autopilot. I've seen it in Google Translate. I want you all to be a little creative. How many of you guys have played the game Categories? No? Yes or no? Okay, so I'm not going to give you guys the full rule book. So what I'm asking you guys to do is in the game, if you have the same answer as someone else, it cancels out. So I want you guys to be a little bit unique and think that someone else already has the same answer and think outside of the box a little bit on some examples that you've seen. So I'll give you guys a couple minutes. Go from discuss. Yeah, y'all can keep talking actually. I'm interject y'all's amazing discussion, unfortunately. And I want to see what you guys have come up with. I want to see right off the bat, what's up? Ooh, I've not seen that before. But yeah, what's up? Yeah, that's a good one. Yeah, yeah. Those are all. Are you getting these ones done? All right, perfect. What's up? Mm, that's a fantastic one. What's up? Object navigation. Yeah, 100%. That too. Any other unique ideas that y'all had? Yeah. Yeah. That's that's great. So I want you guys to realize that this is something a little bit different from I don't know if you guys were here last year, but we had pretty much the basic ones. But the exercise was mainly for you guys to realize that other than the conventional thought of computer vision, there's so many more applications that you see in our day-to-day lives that we kind of glance over, that we kind of don't think about. We just think that, hey, it's here for our benefit. We actually don't see, no pun intended, we don't see how it affects us, and we don't see how it affects the other people around us, right? So what I want y'all to do next, this is going to be something interesting. This is where our meeting takes a little bit of a detour. Uh, that I want you guys, um, I want you guys to talk in the groups that you guys were talking with. I want you guys to come up with a brand new computer vision idea that, not brand new, but something based in reality. Don't make it a bit too extreme. I want you guys to think of a really cool project idea that you'd be keen on making with CV that, hey, maybe before this, you thought, I don't know how to do this, but uh, after this meeting is over, what you guys will walk away with is a full project pipeline and a project architecture for you to actually try this out on your own. So I want you guys to brainstorm some ideas, and us as a leadership crew, we want to take ideas from each group, and us as a leadership crew, we're going to vote for the idea that we're going to carry on with the rest of the meeting for. But that's not to discourage any idea that we don't vote for. That's just for that's more for you guys to take home with it. The architecture will remain the same. So I'll give you guys a couple minutes. Talk with the people next to you. What is the computer vision project that you guys really want to do that maybe beforehand you didn't know, and now with this meeting is something that you want to do? Be creative with it. And yeah, I'll give you guys a couple. All right, all right, all right. My, do you guys need more time, or are you guys good? Uh, more time? You guys have more time. You guys, sorry to cut you out. Do you guys all have ideas? Good ideas. What's up? Animal. Okay. Okay. Animal detection. Is that your idea? All right. We'll come down here. We'll go like that. You guys have an idea or no? Okay. Y'all just, am I memory? Yeah. All right. So we got animal detection and sign language. What do you guys have? Okay. Like seeing the changes between different pixels. Is that what you're saying? We're actually going to cover a little bit about that today. Um, yeah. Like edge detection. Is that what you're talking about? That's totally fine. Keep thinking about it. I'm going still. Uh, you guys have it? Fantastic. Uh, Tommy and Logan. All right, that's a little bold, but in the back. Nice, nice. That's great. You guys. Oh, what's up? Yeah, yep. All right, so not that deep. But I can try. Oh, yeah. It's a great idea. You guys. Yeah, yep. If you guys don't have one, it's totally simple. Yeah, Periscope, like in Silicon Valley. You guys in the back, you guys have an idea, or do you guys just kind of, word. You guys over here, still thinking? That's totally cool. Team, what are we thinking? All right, so food recognition. That's going to be the idea that we're going to go with. Uh, was that? Yeah, the fruit, the ripeness of the fruit. Uh, it's attainable. It's something that we can do, and yeah, that's the idea we're gonna go with for the rest of the meeting. And what I want to say to all you guys with your other ideas are really cool. Hopefully, the stuff that I covered today will help you do that in the future, not just for this. Um, okay, so is it not working? Oh, yeah, fruit ripeness. Okay, all right, so let's get into the meat of it. It was a lot of you guys talking. Now it's going to be my turn for a bit. When we our idea is now measuring how ripe the fruit is. What is the first thing that we need? Anyone? What is the first thing that we need? Someone. Due to the cream sugar. Perfect. We need data. And now this is computer vision. We don't just need data. We just don't need some data. We need a lot of data, like like unquantifiable amounts of data. For as if you want to make this scalable, if you want to make this a lot more robust, we need a lot of data. So how are we going to do that? Uh, well, let's say we're on some new planet and we have a ton of fruit, but they don't have the internet, so we can't web scrape. So what are we going to do? We're going to use a nice device called camera. We're going to take all these pictures. We're going to get all this data ourselves. But luckily, we're not there. We're here. So what can we do? We can just web scrape and we can get the data ourselves, right? We need before I get to that, what we need is ideally in a real world setting, in more scalable applications, you need a harmony. I think that's the best way putting it between your image feed and how you're getting your images and your neural networks and the model that you're trying to use, right? So how are we going to do this? We're here, we have a good number of images, but let's just say we don't have enough. We probably even still might not have enough. What if we see something we've never seen before? What do we do? Well, I'll tell you what we do. We can make our model more prepared by using something. I'm going backwards. We can do something called data augmentation. So what is data augmentation? Well, data augmentation is a way for us to increase the amount of data that we have in the model. So let's say we're classifying fruit in this example. We're going to take that banana of yours and we're going to say, all right, that's a pretty raw banana that's green, but that's the only image I have of this banana. How do I make sure that I can see more variations of this? How can I make sure that my model sees more variations of this? Well, I'll tell you how. Well, I can stretch it. I can shrink it. I can rotate it. I can crop it. I can add noise. I can remove noise. I can do so many different things to this. But I'm going to ask you this question. Does it change what the image actually represents? Yes or no? No, exactly. It's the same image. You're just representing it in different ways. So what is that telling the model? That's telling the model, hey, this is the same thing. You're just seeing it in a different way. Let's open your eyes a little bit to different possibilities and different, variations of what this could be. A green banana might not always be perfectly green. That's more towards the data, but it might not always be in that shape, might not always be of that size. And that's how data augmentation can help us. So keep going backwards. A few examples of this: stretching, rotating, cropping, and you could flip it. I want you guys I want you guys to be a little bit creative with it. Data augmentation has no real boundaries. It's really your imagination of what you can do for this. I want you guys to think of the context in fruit ripeness. Think of some of the ones that I provided. Think of a few more data augmentations that you might be able to apply for this one. We've talked about stretching, rotating, cropping, etc. I'll give you guys 30 to 45 seconds. Talk amongst yourselves or just think to yourself. What are some other data augmentations we can apply to our data to increase the robustness and efficiency of them? Give you guys back. Hey. What is popping? All right. What are some of y'all's ideas? And if it's something new, tell me how you do it. Who wants to go? Or I'll randomly call on someone. Yeah. Say that one more time. I couldn't hear you. Sure. I mean, you can. I don't know what purpose that's gonna help. In in this case, but you can. Yeah. Yeah, that's a really good one. That is a really good one. That's something that comes up a bit, but not it's not very common, but that's a really good one. Anyone else? Blur the image. We're gonna get more into that later. Grayscaling, we're gonna get more into that one later. Yeah, grayscaling is really popular. Yeah, increasing the brightness, decreasing the brightness are very popular as well. Anyone else? Say it one more time. Saturation. Yeah, that's true. Increasing, like, yeah, increasing the saturation. I couldn't find a better word. Yeah, I've not seen that used before. I'm gonna be honest with you, because the way I think about it is, let me show you guys. This picture of this is a warthog. Is this a warthog? No, this is not a capybara. What is it? Cloaca. Okay. So if you look at this, it's not more or that we're rearranging the picture. We're just representing it in a different way, whilst maintaining the integrity of what it represents. You know what I mean? Um, any others? Any other ideas? No? All right. That's totally valid. So we have all of these ideas that we can use. So we can use stretching, we can use rotating, we can use cropping, we can use flipping, we can apply grayscales. We could make it anime if we really wanted to. I don't know what it's gonna do for us. We can do edge detection, we can shuffle the white balance, we can increase the saturation. All of these can really help with our model training. Now, what I want you guys to think about is when you guys do eventually make these projects on your own, is that you cannot pick, which is why I mentioned the anime one and the reshuffling one very loosely, is you cannot pick data augmentations blind. They have to have some kind of purpose for the model that you're trying to train. What is the end goal? You guys should always have that in the back of your mind. If my data augmentation is making an anime, but it looks like the same banana, why do I need to do it? We need to understand why I'm doing it so that the model gets better, right? So I keep going back. Uh, okay, so now we get into a little bit of it gets very heavy, it gets very dense. If you guys want your computers open for this, you guys can have them open because you guys can use it to look them up yourselves as well. Um, this part of the meeting is very I go over a very high level overview. I don't cover any of the math. The mathematics of this it's a bit challenging, and I want to really preface that computer vision is not like a cakewalk. It's not a walk in the park. I still fully don't know it. A lot of us here in this room are not. Just because I'm talking about it doesn't make me the biggest expert on it. It's very deep. It's very dense. What I have here today are some of the feature extractor, some ways to accomplish your goal within the scope that I know how to do it, and not everything, but a good amount. And I want to get into this a little bit, but if you guys are confused, that is completely okay. Please ask, and if I don't know, then please look it up as well. When Google doesn't know, you have a new research project. So here we go. So we're going to get into something called feature extraction and description. So what does that mean? So we have a bunch of these images, right? We've taken our input data, and what we've done is we've applied augmentations to it. Is that useful for the model? All right, yeah, no. We want to get just because it's a banana, our model doesn't know it's a banana, but how does it know it's a banana? What features are we really looking for? We're looking for things like color. We're looking for things like shape. We're looking for things like size. We need to be able to get all of that from an image. How are we going to do that? Well, we're going to use either all seven, which we're going to talk about the dangers of feature extraction and description in a bit. We can use all seven, a combination, or just because there's seven up here, there are not seven in totality. There are thousands. There are infinitely number of ways you can get information out of an image, not just the ones I talked about up here. So the first thing we're going to get into are Fourier transforms. How many of you guys have heard of a Fourier transform? All right. What is it? Yeah. Pretty much. Do you have anything different? Exactly. So when we look at an image, what we can think about is, hey, we can represent this image as not a sum of its frequencies, but through its frequencies, right? And I want to take note of this image over here. We have a dude kicking a soccer ball. I think he's on horse. So what we're going to say is, hey, we want to notice the high frequency components of this image. We want to notice the low frequency components of this image. And the higher the frequency, we're going to get more detail in our spectrum. And the lower the detail, we're not going to get as, sorry, the lower the frequency, the lower the detail we're going to get, right? So how is this helpful for us in the context of uh, classifying of if the shape of the if it's ripe or not. Give you guys like 20 seconds to think. Talk amongst yourselves, and then we'll reconvene. So, how would this be helpful for us? All right, never mind. Okay, are you guys going, or you guys need more time, or just like silent? We're good. Okay, okay. So, how would this be helpful for us? I want to call on you people. Anyone? Any of the same people have ideas? Exactly. So what we want to do is we want to say like, hey, we really want to analyze the important parts of this image and in the context of if this fruit is ripe, we can notice certain patterns within our spectrum that say, hey, that are very unique to it in exactly the way that you described. So that's the easiest, I guess. So what is this? Can you guys tell me what this picture is? Someone's got to say it. Someone just blurted it out. All right. What is this picture of? What was that? What's that? All right. So what we have a model. We want to say, I need to know what the Golden Gate Bridge is. I know what the Golden Gate Bridge is just based off these three pictures. What do you notice about these three pictures? All four of them, actually. What do you notice? That's exactly, they're different angles. I can look at all four of them and I can say, hey, that's a Golden Gate Bridge, even though it's from different angles. How can you tell? How do you know? Uh, yeah, in the back. Oh, sure. Were you gonna say anything different? Uh, not really the zoom, but it's more what she said, where it's the colors and what else did you say? And exactly in the same shape. So I have these three images. I want to classify what this thing is here in the back. I only see these four people in the front. How do you know this still is a Golden Gate Bridge, not like the bridge in Tokyo? Exactly, it's the color and shape. Does my computer know the color and shape of the Golden Gate Bridge? There we go. Not necessarily, and no, not at all, because it doesn't know what it looks like. So we're going to look at classifying. How do we actually do this? Well, we're going to use something. I keep going backwards. We're going to use something called a scale invariant feature transform. How many of you guys have heard of that? All right, exactly. So what essentially we want to do is we want to detect exactly what we were talking about. We want to say that there are unique shapes within the Golden Gate Bridge that make it instantly recognizable. Now we can, and not just from one angle, but from any angle. We can see the spaces between these. We can see the suspension. We can see the color, and we can notice that it is the Golden Gate Bridge. We want to do that here as well. So this is a picture of the Eiffel Tower. This is from the website that I got it from. But imagine it's the Golden Gate Bridge. What we want to do is we want to notice the key points on this bridge. So can someone tell me what, if I'm looking to analyze if this is a Golden Gate Bridge, or can someone tell me what are the dead giveaways as far as shape goes that it is a Golden Gate Bridge? Exactly. Exactly. Anyone else? Yep, yep. Anything else? The gate, sure. Yeah, yeah, exactly. So we know now the reason I want you guys to have this kind of collection of it is so that when we get into the process of it, you maintain the foundation of what we're actually doing here. Yeah. Okay. So how do we actually do this? It's gonna get a bit heavy. So we have the picture of the Golden Gate Bridge. It's got the Eiffel Tower up there. Which you guys to imagine it's the Golden Gate Bridge. We have a picture of the Golden Gate Bridge. What we're gonna do first, we're gonna apply grayscale to it. Why would we apply grayscale to an image when we're trying to classify what it is? Yeah, that's exactly right. So it's what you're going to notice as we continue to go on is that almost all of these feature extractions, not the descriptions, but these feature extractions, we have to put them in grayscale first so that we eliminate some of the background stuff. We only want what we want. We don't want anything else, right? So we're going to apply what is called a Gaussian blur first, and we're gonna apply grayscale. We're gonna apply Gaussian blur. I'm gonna ask a follow-up question. Why would we apply Gaussian blur? Exactly. When I'm trying to classify the Eiffel Tower, the Golden Gate Bridge, I don't really need to care about the things in front of it or around it. I only need to care about what I'm looking at. And it emphasizes what we're actually trying to classify, right? Now that we've done that, we remember what this is called. It's called a scale invariant feature transform. Just based off that definition, what should it be able to do based on this definition? I'm not going to ask this question. What I'm going to say is it should be able to classify that it's a Golden Gate Bridge, the Eiffel Tower, no matter its scale or orientation. So how do we do that? So what we're going to do is we're just going to reshape the size of it. We can make it larger, we can make it smaller. We're going to apply the same Gaussian blur to it. And what we're going to do from there is actually really, really interesting. So we're going to find what is called the local maxima and minima of each point. Okay, I got a bit ahead of myself. So what we're going to do, we're going to take something called the difference of Gaussian. So we're taking of the same size, we're going to take a difference and we're going to get an output. We'd be like, hey, that kind of looks like the Eiffel Tower. That kind of looks like the Eiffel Tower. That kind of looks like the Eiffel Tower. That kind of looks like the Eiffel Tower, right? In a way. Uh, what we're doing is we're eliminating all the unnecessary components and we're figuring out what exactly we need to focus on. Now, from here, we need to find the key points, right? Now, how do we do that? Well, it comes down to, I'm over here. Yeah, so to do that, what we want to do is we want to find the differences in contrast. Because if we have an edge, and if we notice that it's white, surrounding is black or is darker than our pixel point, do we need it? We don't need that point. It can go away. We can just focus on that. We can assign it a key point. And think of a key point as a flag, a directional flag, if you will. So what that means is we're going to say that this point right here is is sloped down, is sloped up, is sloped left, is sloped however which way you want to put it, right? What that's going to do is it assigns it a flag so that when we come back to classify our image here, we can be like, all right, this this one curve here is unique to the Golden Gate Bridge, which is not unique to anything else. It has to be the Golden Gate Bridge. You see this here, you see this up here, you see this over there. It's the same across the board, and we're gonna get our uh, our final classification, our final classification. Do you guys have any questions on that? I know I'm talking. Sure. It's not. It's a good point. It's why they're not very utilized in this space. I wanted to add it just for its uh as a familiar point to bounce off of. But there's a reason it's not added because you're not really getting much out of it. So you make it good. So the reason we do that is because we don't want like if this is a color, if this is in color, you end up getting more information out of it than actually. Any questions on this? Yeah. No. So what you want to do is you, I didn't cover this part, but what it is you have to take like four different samples of it and then you do the subtraction. There's a lot more variation in the math involved when you do the subtraction, but that's just a general way. So you take like let's say you get like four different sizes uh, of this image, and with each size you have four different applications of the blue, and then you do the subtraction with each size. If that makes sense. Yeah. Okay. Where am I on time? Cool, cool beans. All right, let's move on to the next one. Now, every single one after this has its own uniqueness, has its own, but at the end of the day, they're still trying to accomplish the same thing, right? So our next one, maximally stable extremal regions. That is a lot. Can it, has anyone heard of this before? And if you have, where have you seen it? Perfect, because it's not, I wouldn't expect you guys to know. Um, so what are we gonna do? This is a very broad statement. We want to detect stable and unique regions. What does that mean? I'm gonna ask you guys, what do you guys think it means? I want, that's word for word, bar for bar, what I was gonna say. We have a lot of data augmentations we're gonna apply. Regardless of the data augmentation, this one feature is not should be, this one feature is unique across all of them, which makes it immediately identifiable, right? It makes it easily classifiable, easier to track whatever application you're using for, in this case, food records, right? So what we want to do, there are multiple ways to do it, but I'm gonna really just cover the white to black process, the black to white process, because I'm still not fully. It's it's more the inverse, but it's a little bit more than that. But I'm more well versed in white to black. So what we want to do is we want to apply a grayscale as we've done with the rest of them so far. And now what's new? We're going to apply a threshold to this image. Uh, and we want to say values above a certain point, you guys are more important than the ones below this point. So we don't need the rest of you. So what we're going to do is we're going to apply something called a non-suppressing threshold. I believe that's the word, where it's non-maximal suppression. I think that's what it's called. And what that is going to do is that sets these other pixels in the background. They're still there, but we're not applying as much importance on them. And now what we can do is we can just focus on what we have emphasized. How are we going to do that? Well, we're going to use contours, and we're going to use contours to of the connected components. So what remains the same? So we have this picture of a cow over here. And as we go through the image, as we get from white to black, I'm really just want to focus on this part because these first few steps don't cover the process to get here. What I want to focus on is, okay, this cow's shape is most likely going to stay the same as we go forward, or if not the cow, then these sunflowers, and there are specific regions. Maybe it's this middle, I don't know what it's called on a cow, like the foreheads of the cow. We want to identify. We're going to use contours, and we're going to realize that this spot here remains connected regardless of the data augmentation we apply to it. So now that we've done that, we want to find the stability because we said stable in the definition. How do we find the stability of it? Well, what we want to do is we want to measure the perimeter. We want to measure the area of these connected components and realize that, yo, this is almost a direct transformation of our original image, and it remains constant, right? Just because it's been stretched or transformed in a way that it's not recognizable to us it's still a direct transformation of the original image, and therefore can still be instantly recognizable that that indeed is a cow standing in a field of sunflowers. Um, yeah, that's very dense again. You guys have any questions? Uh, yeah, no, this is part of feature extraction and description. So what I want you guys to, if you guys take, if this is all makes no sense to you, which is totally fine, I want you guys to take away the fact that there's a difference between feature extraction and feature description. What we do for majority of these descriptions or these descriptors, it's a better way to put it. What we do is we're extracting, but that means nothing to us if I can't analyze what exactly I'm talking about, right? That's why we have to select the maximally stable regions to identify what they are. That's why we have to map the features to the image so we understand its importance, right? So as I continue to go through these, you guys should realize that, okay, we're extracting, we're doing a lot of extracting, but the last thing we want to do is we want to describe what it is and its significance to us and to the model. Uh, so for the term is Missouri, I think. Put it back. Yeah, Msur. Um, what I'll say is that a lot of computer vision programs in general use a lot of these in the past. It just depends on what, you know, depends on how, depends on its relevance to their application that they're using. Which is why I'm going through all of this is because that you might see relevance for something like this or something that you, and it may not be directly related to something that you've seen, but it might be related to something that, okay, in the future reference that might. So if a region is maximally stable, what that means is that it's easily identifiable regardless of the augmentation you put it at, right? Oh, regardless of the augmentation that you're seeing. So what that means is that, all right, I've got my picture, here's my cow. It's like the fifth time. Okay, so I've got my picture of my cow, right? And okay, we're saying we're talking about food ripeness, right? And we want to see, let's say we have the banana that you have, right? And that's we want to see how ripe that is. We're gonna say, all right, I have the contour of the banana that even if I stretched it, even if I rotated it, does the shape of the banana inherently change? Not really. So if you stretch, it's just a stretch transformation, right? Or if you shrinked it, it's just a shrink, right? That's still a function of the original image. You know what I'm saying? So you can still apply uh, this feature extraction to realize that this image is in fact uh, unique to a ripe banana. Something. Sorry. This is not instead of a machine learning model. What this does is it emphasizes, I should have said this at the beginning. What it does is it emphasizes features that your model can learn to train on. So if you give it an image of a banana, how does it know to specifically, how does it know specifically what that is, right? What we can do is we can feed it more information that we can extract from an image that the model can't do on its own. So that's the big goal with feature extraction, is we want to be able to make our model more efficient. This is mainly for model efficiency, for model robustness, and for model accuracy. Um, and again, if it's not relevant, like I'll ask you guys this question: you guys think it's relevant to this problem, to this specific problem that we want to classify food records? Yeah, it's like so and so, right? So I'll touch back on that point later, but we might not need every. So isn't that wrong? Oh, all right. Our next one. I keep going. We're getting. What's my time? All right. At this point, I'm just gonna keep going. You guys are welcome to stick around with them. So, if not, that's cool. If you guys want. So, uh, our next one: histogram of oriented gradients. That is a word. That is a term that makes no sense. But wait. That actually makes perfect sense. Why does that make? What does orientation mean? Same direction. All we're doing, generally, we're being like, yo, this edge is sloped down. That's all I need to know. That's all you need to know. How do we do that? So, how do we do it? So, first, this is according to the paper for the guys that first developed it. What they did was they're like, okay, we eventually want to get down to like 8x8 cells in my image. So, what I'm going to do is I want to make this image easily divisible. So, I'm going to reshape my image to like 64 by 128. That's not a requirement. That's just a suggestion that makes it really, makes it optimal, right? So we're going to reshape it down to 64 by 128. Then we're going to calculate the gradient of every pixel in the X and Y direction. We're going to use something called a Sobel filter. Have you guys heard of that? Exactly. So what we want to do is this filter is going to go through our image and be like, all right, we're going to take our image at the top, we're going to subtract it from the bottom, from the left to the right, from on our diagonal. So we want to get all of this information and we're going to assign it to the X, we're going to assign it to Y. We have two new matrices. We have an X matrix and a Y matrix for our gradient. And how do we find the angle? We just do the arc tan or the tan inverse of Y over X. And that's how we get our gradients. Oh, yeah. So are you guys with me so far? Am I losing you guys? Yeah. Okay. Please do ask me. All right, so we're going to get the magnitude of each. So the magnitude is going to be higher if there's a change in intensity or really a change in contrast because we have grayscaled our image. I just haven't mentioned it here. Then what we're going to do is we're going to calculate a histogram of the gradients in 8x8 cells, which is why it is important that we are in 64 by 128. Will it help if I draw it out? Yeah? Yes? All right. I appreciate you all being here in the long. No, whatever. All right, all right. So we have an image, uh, like this. All right. So we're in a spot where we've calculated all of our magnitudes in the X and Y direction. So what we want to do now is we're taking cells in 8x8 cells. So we're gonna pretend that each one is 8x8. All right, so pretend each one is 8x8. We've done a Sobel filter, and for this case, we've used a 3x3 filter, which means that you're going to have 9 bins for each one. Depends on the filter that you have. So we have 9 bins, and we're using an 8x8. So this is just one, right? So what we're going to do is we are going to calculate, we're going to normalize each cell, and we're going to sum up. There's more to it, but essentially we're going to sum up the features that we see in each image, right? The amount of edges kind of in a way in each image. And what we're going to do is we're going to sum them up for each one. All right, we're going to do that for each 8x8 cell. That's a lot, but wait, hold on. We're gonna make each cell bigger next time. We're going to use a 16x16 cell next time, and we're going to do that for each one. And then we're going to continue to make it bigger until we've reached the maximum size of our cell. But while we do that, what we want to do is we want to make sure we want to get the features of the entire image. Once we reach that point, we're going to get the features for the entire image, and then we're going to compare it to what we've had already. So if our numbers stay the same for majority of it, that means we have better results. That means our model will be better. If it's not, then you have a little bit of tweaking to do as far as calculating this a bit better. So that's the histogram of oriented gradients. Do we have any questions on that? It's a graph, but it's more, and for our case, it's more of a way to represent what we have, and more of a way to compare uh, across our images. Yep. Yeah, that's yeah, that's a better way to put it. So we want to sum up the frequencies and more importantly the directions, which is why it's like a histogram, right? We're calculating the frequency of the direction, and then once we want to continue to do that, we want to compare histograms across as we continue to increase in size of our circle. All right, all right. We're speed running. What's my time at? How at 6:10? Oh man. All right. This part is a bit easier. It's placed here just so you guys get a little break. We've all done k-means clustering. We've all done k-means clustering. That's all color histograms are. We want to get the frequency or the amount of times you see of certain pixel intensity in each image. And we're going to use k-means to cluster all of the colors into a certain spot, and we create our histograms. No questions. Okay. All right. Next, texture analysis. I brought a rock as a prop, but I don't think that I don't think we need to use that. Actually, yeah. Can you pull out the rock? It's in my bag. It's in my bag. It's by it's down. It's down there somewhere. You know, just leave it. Just leave the rock, man. Who's gonna? You found the rock. Let's go. All right. Oh my god. Okay. All right. So based on this rock, all right, I got this rock hiking in Yosemite. Now that you guys need to know the details, but I got this rock. I thought it would be really useful for this slide. Based on what you see, all right, is what can you classify the texture as being? Rough, right? It's rough, but our computer doesn't know that. Our computer is going to separate the types of textures between tactile and visual. So tactile means that it's sensitive to the touch. So that's what I'm feeling right now. It's smooth, it's slimy, it's rough, it's whatever. And our visual means it's what you guys are seeing. It's your impression of the rock. What if this looked like this, but it was actually smooth, right? That's what we want our computer to do. How are we going to do that? We're going to use something called a gray level co-occurrence matrix. um, Pretty much what that is, we're just going to be like, yo, this looks kind of rough, and we see that the whole way. So it means it must be rough. So that's, or if it's smooth, it looks smooth here. We're going to compare it with the rest of the image. This compares with this, therefore it's smooth, therefore it must be smooth. So it's a way that we can classify. So maybe your banana is smooth, but it becomes rough, and maybe that's what a fully ripe banana looks like, and therefore we see some kind of use case. Or like with the pineapple, right? Or something that starts smooth and ends up prickly. I don't know. Okay, I'll keep going. Edge detection. This is my last one. Thank God for you guys. Okay, edge detection. Something called canny edge detection. This is the most popular one. We're going to grayscale the image. We're going to apply a Sobel filter, and that's really all that there is to it. Yeah, that's really all that there is to it. We're going to apply a threshold and be like, all right, we're going to measure the contrast. This is more important than this, therefore this must be an edge, and we can create an image like this at the. So those were 7 feature extractions and descriptors. I'm not going to ask you guys to discuss how it could be used for this project, but you guys can think about it and can take something home with you that maybe I can use one of these for that. All right, so wrapping it up. How many of you guys have heard of resonance? I just need to know if I need to do this one. Who wants me to cover it? All right. Okay, so that's totally fine. So ResNets, it's the reason I'm talking about ResNets is that there's this really serve as like a foundational block in computer vision. It's not really what they use now, a lot more, but for your purposes and for your projects and at a smaller scale, you can definitely use this or its variant. So what we want to do is, so firstly, it's very, very similar to a convolutional neural network. Its output is f of x plus x, where f of x is like the output of a CNN and x is the input into the residual block. So why are we doing this? Well, we want to eliminate the vanishing gradient problem, and it allows the networks to scale while reducing that problem. Yeah, yeah, okay. Okay, so that's just one. If I really wanted to, I could have talked about all, but I chose to talk about the other stuff instead. So You guys all know about convolutional neural networks, support vector machines, ResNets, but the ResNets have its own variants that came out like 10 years ago. There's ResNext, there's DenseNets, there's wide ResNets. There are other machine learning models. There's a YOLO, which you do only live once, but you also only look once. Single shot multi-box detectors, mask RNNs. You can use transformers. You can use GPTs. You can use something called pix to pix. This is only 12, but there are like thousands. So like, if you guys are really interested, please, you can go through this whole thing. You can see where it's helpful for you guys. You guys can continue to explore. Uh, I hope uh, I hope this meeting gave you some kind of an idea. I hope this hopefully piqued your interest. Maybe you don't understand it now, but maybe you can in the future if you guys are that interested in it. There are so many more models. There's so many more actually, there's so many more feature descriptors. There's so many more data augmentations. There's so much more that you can do in this field that I haven't even I haven't even talked about. I haven't even touched the surface. So if you guys are really interested, take the time to look at it. But we guys do have a pipeline for creating this fruit ripeness computer vision project. What are we going to do? We're going to get the data. We're going to apply data augmentations. We can pick our different feature descriptors, input that into a model of your choice, and we're going to get great accuracy and great efficiency as well, which is a big problem in computer vision. Is the efficiency. We have a lot of data, but our predictions are not that fast, right? So that's a research project for you guys. So with that, I want you guys to try it yourself at home first.
Okay. Good morning, everyone. That was quite the thing. Before I move on, who learned something? Who learned something? Awesome. Okay, then in that case, this was a success. This was a success. Who is going to go home and lie in bed to try and recover some of the mental state that they had before this meeting? I know I am. So that being said, we're going to move on to a little announcement before the end of this meeting. So, look alive. We're done with the math and theory. Now it's just some fun further club stuff. So, sky is no limit. A couple of you guys saw the form that was sent out. First of all, raise your hand if you know what the Sky is No Limit challenge is. As I see some familiar faces, some unfamiliar faces. Okay, so before I move on to the theme, the Sky's No Limit Challenge is something that this club does. It's a quarter-long competition where you create your own AI model, ML model, based on a theme that we give you. We have workshops to help walk you through, so if you've never done AI or ML before, no worries, come to the workshops and we will help you through. If you have done it before, I don't need workshops. I don't need the intros. Go ahead and work on it on your own, but still feel free to come to the workshops. I'll answer any questions. We're always here to help. So the theme for this quarter-long competition, Sky is No Limit, for this quarter is going to be Rainbow Road. So as usual, you can take that however you want. You can take the word road, do something with cars, take the word rainbow, do something with rainbows, take the word Rainbow Road and do something with Mario. The world is your oyster. Is that the word? You know what I mean. Rainbow Road is the theme. Good luck. And also the workshops are going to be on The workshops are going to be on Mondays from 3 p.m. to 5 p.m. I will be walking you through all the steps of creating your own ML model, from finding data to creating it to training it and fixing it, testing it. We've had some really, really amazing projects in the past, and I really look forward to what you guys create this quarter. So again, sky's no limit, Rainbow Road, quarter-long competitions, quarter-long competition workshops on Mondays, 3 to 5 p.m. here in Engineering 2. Specific room in Engineering 2 to be determined, but that will be hopefully released soon. Yes.
Perfect. All right. So there was going to be, so yeah, before I get into it, if you guys could please give me feedback, please give us feedback. This is a very new style of meeting. I really want to get your take on it. It'll help us, it'll help them for next year. And if they want to do something similar or take elements like this and move it to some of their meetings, maybe not the whole thing, but some of them too. So there's a QR code. The link is bit.ly/cv-sky. Can you put it down on the, yeah, just because I want to move on. Okay, so there was going to be a coding section, but it's like way past time. But what I do want to, I'll keep that. I go back. Okay, so it's over there. So bit.ly/cv-sky. So what I want you guys, or uh, to try it yourself, this is the project that I've written up for you guys is nothing, has a lot of the stuff that I've talked about working in the background. So you, while we're just calling libraries, they're doing a lot of the data augmentation. They've done the data augmentation and feature extraction and all that jazz behind the scenes. So this is a really fun project for you guys to track your hands and do some like, all right, this is a pinky, and no matter where it moves. So click the link, go to the link, it will get you to a collab notebook. You can either download it to your IDE, or you could copy and paste the code into your whatever IDE you pick. And can you write this one down too? tinyurl.com/sky-cv/code. All right. And then a note. So this is hand tracking. Who here has a Mac and an iPhone? Okay, so one thing to note, when you guys run the code, if you guys have it synced up to your phone, make sure that you know that when you run it on your Mac, it might open the camera on your phone. And you'd be like, hey, this is not working. I'm getting no values up in my terminal. What's going on? Well, the reason is because it's opened your phone on your iPhone's camera. So what I do is I just power off my phone, and then I do it. But if it works for you, it happens only in a few cases. Only a few cases. The second thing, how many of you guys are on M1, M series Max? Okay, so what you guys need to do, so this uses a library called MediaPipe. I don't think I've written it, but I'll put it in the Discord for you guys to see afterwards if you guys want to try it out. So when you install MediaPipe, you do not install just MediaPipe, you install MediaPipe-silicon. And that will allow it to work on M series Max. But for everything else, just pip install MediaPipe. And yeah, if you see the code, it's only like 3 fill in the blanks you got to fill in. It's not that difficult. So yeah, have fun with it, and you can use it as a foundation to really do like a sign language project, and, something like that. Yeah. Oh, not in the import statement. So when yeah, yeah. I'll will it help if I just wrote it down here? We can just end it, and then you guys can. All right. So, oh yeah. No, I was just gonna close it. So with that being said, that's our meeting today. Thank you guys for being here. And yeah, so thank you. If you guys have any questions, I'd be happy to answer them. If not, have a great rest of your week. And a wise man would take some of the stuff and use it for your sky's no limit, but that's just me. That's just me. So,